a sphere. Sometimes this is where you get to the spherical harmonic functions, or sometimes this is called the spherical harmonic. We'll talk about what that means in a little bit. Okay, let's talk about what our system actually looks like. I'm going to try my best to draw a sphere. So this is like the equator. These are the, what is it? Meridian, Greenwich lines. Does anybody know where the what was that? Yeah, longitude. Latitude, fatitude, that's how I remember it, longitude, long. Arctic Circle, anybody know what degree the Arctic Circle's around? Yeah, exactly. Wow, that's spot on. We had this conversation because one of my chemist buddies last night, he went up to the most northern part of Alaska in the United States to study brominated and chlorinated things. And we started talking about refrigerants. And we were talking about the northern lights. And me and his wife were arguing that he was wrong about where the Arctic Circle was, because we felt like that was too slow. And he's like, I've been there. What do you guys know? And he was right. Okay, so that picture makes somewhat three-dimensional sense, right? Okay. So we're going to consider a particle with a mass, a quantum particle. M. That's free to move any direction on a sphere with a radius of r. The potential, just like particle on a ring, it could be any arbitrary value. What value would you pick? Yeah, that's what I want to go with too. The potential is 0 on the surface. Okay. I need 3 colors. What variables do we need to describe this thing? We could do it in Cartesian coordinates. So what symbols do we generally use for Cartesian coordinates? Yep, X, Y, and Z. We don't want to do that because it makes separation really hard. What's the other things we could pick? Yep, R, phi, theta. Yep. Okay, R is just the distance to the point, right? What color do we want to express R with? Red? Okay. I lied. We're going to go with yellow. Okay, so here's our particle. That's R. Okay, so particles at this point in space. My arm is the origin. What other thing do we have to indicate? Yep. Phi is this angle in the line of the equator. So like, where is it in regards to that coordinate? That's why I wanted to leave red alone. So there's phi. What's the other thing we have to indicate besides this and the distance? Yep, the angle up. That's our theta. Is this angle along there. I know I crowded that picture, but does that make sense to people? Okay. You good? Okay. We're going to need all of those things. The nice thing is R is not changing, which will come to our advantage when we start looking at differentials. So we have this quantum system. What's the first question we always ask with our quantum systems? Yeah. What does the Schrodinger equation look like? What does the Hamiltonian look like? Then we use that to find the wave functions. So what does the Hamiltonian look like? I'm going to shorten Schrodinger equation to SE. Generic equation for Schrodinger equation, even though I've given half of it away. H hat. Yep. Okay. Typically, how do we break our Hamiltonian up? Yep, potential and kinetic energy. Okay. Kinetic energy, how do we always express that one? Yep, partial derivative of stuff. Let's do it just in Cartesian coordinates right now, and then we'll change to spherical polar coordinates. What is it for Cartesian coordinates? Yep. Second derivative of x, second derivative of y, second derivative of z. Okay, plus, we typically have the potential term. What have we set the potential to in this system, though? Yep. Nice. We'll get that. Okay. What's another way we can represent this thing? We had another symbol. What was it? Yes, yep. Gradient. So we can represent this guy. Oops. Like that. Okay. You can try your best to make this work with Cartesian coordinates, but what you're going to find is they're connected to one another. It's not easily separable. If you go to spherical polar coordinates, it is. Am I okay to erase this picture of our system? We might need it again, so I'll have to draw it again. This thing, it looked very ugly for spherical polar coordinates. I said it comes from just doing some trig. You should have done it in calculus to figure out where it comes from. Maybe in physics too. I'm not going to have enough space. Why did I start it this way? Oh well, we'll go with it. I'll erase some of this to make it look a little better. Okay. This is for any spherical polar coordinate system. Can we simplify this for our model? Is there anything that we're fixing in our system? Yeah, R is fixed / constant. What does that mean for any of the stuff in here? Yep, because what's the value of it if it's constant? Yeah. Okay, therefore, what happens to our gradient? Yep, so what happens to this term? Gone, donezo, because it's 0. What about these other guys? Yep, they hang around. So that becomes, let's write it all out one more time. Theta, second derivative of E, like that. Now we've dropped the R term, and since doing that, we're going to be able to change this symbol up a little bit. Let's plug what we have here into our Schrodinger equation, and let's see what we get. Get negative h bar squared over 2m rho 1 r squared sine theta phi squared theta. Was that right? Yeah. All right. Okay, still looks complicated. Is there anything we can do to simplify this? Anything we could pull out from this expression? Yeah, we could do that. I don't know why. Oh, we're going to leave the sine theta for reasons unknown right now. But you're right, we could have pulled the sine theta out. Problem is the sine theta is changing. So we're going to leave that one alone. But R is fixed, right? So we can pull that bit out. So what we're going to get in that beginning part is 2mr squared. We showed a relationship. Do you remember what that symbol I meant? It's moment of what? Yep, and it was defined as mass times what? R squared. So we could simplify this a bit more. Get negative h bar squared over 2 what? Yep, I then we would get all this other junk. Okay. This thingy, we're going to give it a new symbol. Is that lambda? Yeah. I only remember it from Revenge of the Nerds, if anybody ever watched that. Okay. So therefore, we could write this a little bit simpler because this is taxing to write a million times over and over again, and we're going to have to write it a bunch. So it's a more convenient way to represent that. Okay, we have a Hamiltonian. We know what it looks like. We've derived an expression to get our energy. What's our next step? Yep, we gotta find the wave functions. So, oh no, da. All right, story time, sorry. I'm feeling a little bit under the weather because my friend brought his sick kid to my house. He was like 1 year old. The reason I'm talking about this is he was like sort of like, he got away from his dad. I was by the swing set, and this kid got to the set of stairs, and little baby waddling towards the stairs. I felt the same way with that chalk that I just did, like, oh God. But the kid was super sick, like snotty, everything like that. For a second, I was like, I don't know if I really want to touch this kid, but I caught him. It was all good, but now I'm sick. So no good deed goes unpunished, right? That's why I'm surprised you want to be a dentist. Like, that sounds like, oh God. I just need hand sanitizer all the time. Okay, we got to figure out psi, and we got to figure it out from this thing. Everything we've done has been in an attempt to make it into an easy differential equation, which sounds like the biggest oxymoron ever. How would you manipulate this equation around to get to something that looks more like an eigenfunction eigenvalue problem, or one that's easier to solve through your techniques you learned in differential equations? Yeah, move all this crap over here. Then you leave all these series of second derivatives alone, and you know you have to have something. What's this side going to look like after I move everything over? Yep. Okay, this is going to get annoying to write over and over again, so I suggest we just make a new constant. Do I have the ability just to call this a new constant? Yeah, nothing's changing. We're going to call this guy epsilon. I think that's the right way of epsilon. Yes, it is. Okay. Now we're going to ask a series of questions we're going to try to figure out what we can do to make this differential equation happen. So my first question is based upon all of this stuff. What does psi depend on? So what's it really a function of? Mm-hmm. My next question is assuming the wave function is separable. So let's assume we can break apart psi into separable equations, or it is a separable equation. What does that actually mean? Or how would that benefit us? Right. So we would say we have two functions. What's one function going to depend on? Yep, theta. And what's the other one going to depend on? Okay. So if they are separable, capital theta, that depends on little theta. And then we have capital B, that depends on that guy. I don't know, a couple of years ago, they said this one looked like a chubby kid. Here's the chubby cheeks, and there's the smile. I didn't really get it, but that's what they said. That's what it looks like to me completely. It's like hero, nondescript superhero. Oh, they saw chubby kid. Okay. We want this to be true because it makes our lives easier. However, we haven't proved it to be true. What do we need to do to show that this is true? What should we do with these things? At least for our specific system. Yeah. We got to plug it into Schrodinger equation. And we got to show, yeah, in fact, we can separate things out. Okay. This is where we're going to have a lot of algebraic manipulation. If a symbol doesn't look quite right or you're not sure what we're writing down, yell at me so we can correct that. But we're going to apply separation of variables like we did for a particle in a 3D box to our system. Make it work. Okay, so we want to start with our differential equation that we determined. And what does psi depend on again? Yep. And then, oh, I think we put the negative sign in there. We're going to leave the negative sign out for that guy. Reasons we'll talk about later. Okay, what would you do next? Could have been timed better. Yeah. We're going to assume we can break this guy apart. We don't know if we can do this yet, but we got to try it. Once we do that, then we can plug everything in and we can see if it can work. And you're exactly right, Ellen. Okay. So now all we're going to do is we're going to take this guy, this lambda squared, and we're going to write everything out associated with it. So we got 1 over sine. Did I leave out a sine squared in some of these things? That's where I went wrong. So it should have been a sine squared in half of this stuff. I'm sorry. Oh, no, we did that, right? Or did I leave stuff out? Should have been a sine squared. I'm sorry. Then we got the second derivative of which species? Or phi, yeah. Or parameter. And we're going to apply that to our theta. Or phi. Then we got plus 1 over sine theta. Which way do operators always act? Yep, to the right. So there's a derivative with respect to theta here, then a sine theta, then another derivative with respect to theta, right? Which one applies first? This guy or this one? Yep, this one goes first. So we're going to put in this capital theta, capital phi, and that guy. Eventually, this other one will get applied. Oops, except I forgot theta in there. Man, I'm doing bad today. Sorry. I'm going to rewrite that. So we would do this derivative first, then multiply a sine theta, then do another derivative. Make sense? Okay, and what's all of this equal to again? Yep, negative E psi. Or at least, might be better to break this thing apart into capital theta capital phi. All right, we're going to talk about one more thing, and then we'll be done for the day because we're going to have to basically redo this portion next time. Tomorrow, lucky you, hit twice in a row. Okay, what do you notice about this differential here? Is there anything we could do to simplify that? What are we taking the differential with respect to? Phi. Okay. So this portion, does it apply to that guy? No, this is just a constant with regards to the differential. What does it apply to? Yep. When we look at all of this stuff. First derivative, what does that apply to? Does the phi get involved at all? What about with the second one when we multiply sine theta in? Does that impact the second derivative with respect to that guy? No, because it's just multiplied by, right? So we can still pull out this phi. So even this stuff here only applies to that guy. We have one more step to truly show that they're separable. We're going to divide through by these things, but looking at it right now, is it separable? Yeah, these terms, even they're just multiplied together. The differentials don't impact these other functions. So yeah, it is separable. To be a little more mathematically rigorous, we got to divide through by this stuff, and we can show that next time. Okay. Are there any questions so far? I gotta fix my notes. Just remember squares everywhere. You're going to have to try to show this on your Quizlet, so know how to do that and go through it relatively quickly. Okay? We talked about degeneracy when it comes to particle on a ring. We defined a new system, particle on a sphere. And then the mathematics, even though it looks scary, what we're going to do is we're going to use that table that I handed out earlier today and information from particle in a ring that we've seen in the past. Okay? Are there any questions right now? Okay, be joyous. Once we're done here, we get to talk about actual atoms, and then we'll move to molecules finally.